Okay, so I don't know how well you're going to be able to see things, but we're going to attempt to show you, the ones who are not here in lab, what the titration lab looks like. So what we did in lab today, if you weren't here, is we did a titration lab where we calculated what the concentration of the unknown acid is in this flask, sorry, and we used it by titrating it with a known molarity or concentration of a base. So basically they're going to do a reaction in this Erlenmeyer flask, okay? That's what I was trying to name this, a volumetric flask. This is a volumetric flask because you really only use one. If you look at the notes, you only use one little tick mark, and that's this copper looking one right here. And basically once you fill it up, it's 100 milliliters. But anyways, so we're going to titrate it. So what we're doing is we're going to take, let's see, from this right here, this is the base, and this will be the acid, okay? So when we're doing a titration, it's best that we know the volume of something. So the beginning volume of this, we're going to add acid first. So the beginning volume of the acid is 35.55. 35.55. 35, yeah, 35.55, and we're going to add about 10 milliliters, okay, of it. So we're just going to open this, okay, and add about 10 milliliters of it. It's down to 40, 41, 42, 43, 44, 45-ish, okay? It doesn't have to be perfect. And then we're going, so we have acid in here and it's clear. And we're going to add some phenolphthalein solution, okay? We're gonna add a couple of drops to this. Okay, just a few drops is all we need. Okay. And what this does is it turns pink when the solution is basic, okay? So right now it's obviously acidic and it's clear in an acid environment, okay? So we're going to add some base to it and see if it turns pink at all. So I'm actually gonna pick you guys up. Okay, so now we're under the base one and we're going to titrate it until it kind of turns pink. So here's the stopcock, they say, and you just turn it, and it should add some base to it. Okay. Once the pink kind of persists, you want to kind of turn it as you go. Okay, not there yet. For those of you who have done this lab, you see how annoying it could be if you do it too much. Once the pink kind of takes a while to kind of go away, you want to kind of go a little slower. Not yet. Not yet. We're looking for a persistent pale pink color. And then it's very easy to overdo for those of you who have been in lab and noticed. Not quite there yet. It's persisting. So at this point we're going to do one drop at a time almost. Well, that's not a drop, but let's see. It's a pretty pale pink color, and it disappeared. So we're going to add another drop or two. It's pretty pale pink. I'm okay with this. So we do it, and so what this indicator shows is that it is slightly basic. So we've added just a little over the pH of 7. So, and our end points, okay, we look at the graduated cylinder, not graduated cylinder, the, what's it called? Burette. see, it's trying to focus on everything but the burette. There we go. I would say it's like 43.95. I don't know. 43.95 is the final volume. So I'm gonna take you back. Okay, so a titration, what you just saw is a titration lab where we take a known concentration of an acid or a base. I could have easily switched between acid and base. So a known concentration and a known volume, and compared it with an unknown concentration and a known volume. Okay, so basically in this specific lab, we knew the concentration of the base, okay? We were looking for the acid's concentration, okay? So we knew the concentration of the base, which is 0.1 molar. And the known volume would be whatever the final minus initial volume is, okay? That would be the known volume. And then the unknown concentration, we don't know. The molarity of the acid, we didn't know. Okay, and the known volume of the acid, we put about 10 milliliters, but it would basically be volume final minus volume initial is equal to the volume of the acid. It's the volume of the base. And so what we did was we calculated this by taking the molarity of the base, okay, and then we plugged it in, multiplied it by the volume of the base. Okay, and then we set it equal to the molarity of the acid, which we don't know, times the volume of the acid, which we did. Okay, so the actual equation was molarity of the acid is equal to molarity of the base times volume of the base divided by volume of the acid. Okay, and we just plug those numbers in, and that's all titration is. Okay, you saw the experiment. I didn't write down my volumes, but you could actually calculate that if you wanted. If you plugged in the volumes that I said on the video, you should get the molarity of acid at about 0.12 molar. So that should be your answer if you wanted to calculate and compare. But that's basically titration in a nutshell. I showed you the video of it. So yeah, so let's go over some titration questions, okay? That's probably what you want to know. So some titration questions, let's start out with one and maybe do a couple, I don't know. In a titration, so in the lab, guys, if you weren't there in the lab, the kids were given this equation right here, okay? They were given it, so, and all of the coefficients are 1. So that was an easy part, but in your test, it won't be like that. You're going to have to come up with the word equation and balance it. It'll give you the acid and base that you're dealing with, but you have to kind of predict products and balance it yourself. So number 1, it says a 25 milliliter solution of hydroiodic acid is neutralized by 37.5 milliliters of a 0.188 molar potassium hydroxide solution. Basically what it's asking is what is the concentration of the hydroiodic acid, okay? So how you solve this, first you must write the word equation, okay? So you have, actually it doesn't, we can write the formula equation is fine too. So HI, okay, is combining with KOH, okay, and the products, this is a neutralization reaction, so the products will always be water and a salt. The salt is the metal and non-metal from the acid and base, so it would be KI. Okay, K has a +1 charge, iodine has a -1 charge, so they're 1-to-1 ratio. So now we just have to balance. So we have the hydroxide broke up, so we have 2 hydrogens here, 2 here, 1 oxygen here, 1 here, 1 iodine, 1 potassium. So it looks like it's already balanced for us, so that's easy. So now there are 3 steps to solving a titration problem. first you have to find the molarity of what you know. So we know the concentration of this and the volume. We need to find its molarity. You need to find its moles by using the molarity calculation. So you use M equals moles over liters. The second equation, or the second part, you use stoichiometry. Because we didn't use 1 mole of this, we used this many liters, which we have to calculate how many moles. And we don't know how many moles of this solution it is, so we have to do stoichiometry. So number 3, after we find the moles of hydroiodic acid, we can calculate the molarity of it, moles over liters. So just so you know, how was I supposed to know those 3 steps, okay? So if you'll look here, the 3 steps you wouldn't have, okay? So if we were to try to just solve it immediately, the question says, what is the concentration of hydroiodic acid? So we know that there's 25 milliliters. We have to convert that to liters. So to find concentration of hydroiodic acid, you use moles over liters. So we know the liters, right? Okay, liters, it said 25 milliliters. So we actually need to convert that to 0.025 liters, okay? We're trying to find molarity. What we're missing, moles. We're missing it. We don't have it. We don't have grams of it. We don't have anything that we can use to convert moles to anything to moles in the question. So we have to calculate the moles of it, okay? And to calculate the moles of it, we need moles of something, okay? So here we can actually find moles of the potassium hydroxide, okay? That's why we use our first step here. Once we find moles of potassium hydroxide solution, it's a 1-to-1 ratio. Then we'll have the moles, that's where we use this. Then we'll have the moles here to plug in, and we can actually solve what we were trying to solve in the first place. So these type of problems will have 3 steps to them, okay? So first step, we need to find moles of the solution that we know more about, okay? I'll zoom in. Okay, so to do that, we don't know, we know molarity, so 0.188, okay? We know the molarity. We don't know the moles, that's what we're trying to find. And the liters, okay? Liters, you can just move the decimal over 3, so it'll be 0.0375 liters. Okay, and then we just need to manipulate the problem to get our moles. So you would just multiply 0.0375 on both sides, 0.0375, okay, and that will give us our moles. Moles of KOH, okay? So you just type it in the calculator, turn it on. So 0.0375 times 0.188. We have 7.05 times 10 to the third. I don't like dealing with these exponents if I don't have to, so I'm actually going to write it out. So it's going to be 0.007. So 0.00705. Okay? That's our moles of KOH. Now we need to plug that in and find out, basically we already know it's a 1-to-1 ratio, but I still want to show you the steps. So you would take this answer and bring it down here, 0.00705, okay, moles of KOH. We need moles of HI. Okay, so we need to cancel out moles of KOH. Okay, and to do that, we grab the coefficients up here, which they are both 1. Okay, so then our answer is 0.00705. It's not always the case. Okay, it just happens to be that this is a 1-to-1 ratio, and I'll probably move on so that we have, or move to a different, more difficult one, so that you can see one without a 1-to-1 ratio. So now we have moles of HI, and at the beginning of the problem, that's what we were missing. Okay, so we just plug it in here. So molarity will equal moles, which is 0.00705, divided by the liters, which we grab from the problem here, which is 0.025 liters. Okay, and we just type that in the calculator, and we have our concentration. So then we put 0.00705 divided by 0.025, Okay, so our final answer, the molarity of hydroiodic acid, the concentration is 0 point, and we need two significant figures, so 0.28. And that's your answer. That's how you solve concentration equations. Let's do, usually they're more difficult as you know what, I want to do the back one. That's the one I didn't really have a lot of time to do in class. So let's do it now. If you don't have time, I don't care. You can skip it or whatever. It's all up to you. You know how well you know it. All right, so let's just go on with this one. So we have this equation, okay? There's two parts of it. This is more like what you'll see on your test, okay? There's two parts of this. There's part one. It's a whole different chemical equation, part one, and then we don't have enough information in part one, okay? It just gives us two volumes and that's it. We don't know the concentration of either of the solutions, and we cannot find out any answer unless we do. So the second part of the question actually has all of the information we need to find the concentration of this thing, okay? So there are two equations going on. First one is HCl is neutralized by MgOH, magnesium hydroxide, okay? So it's neutralized by that. Second equation is MgOH is being neutralized by H3PO3. Okay, so that's the two equations we're dealing with. We have to do this one first, okay, and then this one second. This one we have enough information to find the molarity of this. Once we have the molarity of this, we'll have volume, and molarity, and so we just have to find molarity of that, which is what the question's asking for. What's the concentration or molarity of hydrochloric solution? So in order to solve this, you first have to predict the products of both of them, okay? So these are both neutralization reactions, okay? There's our acids and here's our bases. Bases are the same thing. So when you have neutralization reaction, always you have H2O as the product. And then you have the salt from the acid and base reactions. So here it would be magnesium chloride. And magnesium has a +2 charge, chloride has a -1, so it'd be 1 and then 2. Here, POH has a -3 charge and magnesium has a +2, so it'd be magnesium 2, 3, because PO3 has a -3 charge, and then PO3, 2. Okay, so now we need to balance it. So we have, I don't want to get these confused with coefficients. All right, so we have one hydrogen. Let's not do hydrogens, let's do chlorines, okay? 2 chlorines here, 2 here, okay? 2 hydrogens plus 4 hydrogens, so we need a 2 here. Magnesium, we have 1 and 1. Oxygens, we have 2 and 2. Hydrogens, 4, 4. So I think we're balanced on the top one. The second one, we have 1 magnesium, 3. Hydroxide's broken up, so let's ignore that for now. Let's balance the PO3, 2. We need 2 here. Okay, magnesium 3, oxygens we have 6, so we need 6 here. Hydrogens we have 6 plus 6, which is 12, so that balances. So this is now balanced, okay? So we have balanced equations. Now we can actually start the problem. So the first part of the problem, we're going to have to find out the molarity of magnesium hydroxide. So again, 3 steps, 1, 2, 3, okay? We're actually going to have to do this twice. Okay, first to find molarity of this one, then we can use that to find the actual answer to the question. Okay, all right, so we have, we need to find first the moles of this that's being reacted, okay? So we need to find the moles. We have molarity and liters, right? If you look in the question, we have molarity of it and liters of it, okay? So we have 0.20 equals moles over 0.0300, okay? So we just multiply that on both sides. Okay. So 0.0300 times 0.2. And that's 6 times 10 to the negative 3. So 1, 2, 3 moles of H3PO3. Okay, so that's our how many moles are reacting. Now that we know moles, we can do our stoichiometry. Okay, and we start out with this, so we can find moles of that. So 0.006 moles of H3PO3 times, we need to cancel out moles of H3PO3 and get moles of magnesium hydroxide, MgOH2. Okay, so now this is where we grab coefficients. Last time it was 1 to 1, but this time it's not. So here it's 2, here it's going to be 3. So then we just plug that into the calculator. We take 0.006 times 3 divided by 2, and that equals 9 times 10 to the negative 3, so 0.009 moles of MgOH2. Okay, then we need to calculate molarity here, and we'll have molarity of this, and then we can do the other side. So molarity is equal to moles of this. Okay, so M is equal to 0.009 divided by the volume, which it says is 0.050. So molarity is equal to 0.18. That's the molarity of MgOH. Remember, the ultimate question was to find the molarity of the HCl solution, okay? So now we know the molarity of the magnesium hydroxide. We can plug it in here and do the same thing, but our ultimate outcome is to get this for hydrochloric acid. Okay, so first, again, we start with molarity. Okay, so molarity, moles over liters, for the first question now. Now we're looking at the first part of the question. So we have liters of HCl, which is not what we're looking for. Liters of, so our molarity is what we got down here. Okay, we plug that in up here. So that is 0.18, okay, equals, sorry, that's molarity, moles over liters, which is 0.0780. Okay. Then you just manipulate the problem. Okay, you're going to multiply this, multiply it. Okay, so we're going to get 0.0780 times 0.18, and we will have moles equal 0.014. Okay, so that's moles of MgOH2. Okay, now we have moles of that. We need to get moles of hydrochloric acid. So 0.014 moles of MgOH2. Okay, we need moles of that down here. And we'll have moles of hydrochloric acid. So we need to look up here and find the mole-to-mole ratio. So this will be 1 and this will be 2. So basically we take this and multiply it by 2. I know it's 0.028, but I'm going to do it anyways. 0.014 times 2 is equal to 0.028 moles of HCl. Now we know moles of HCl, we can calculate molarity. So 0.028 moles of HCl divided by its volume, which is 0.0250. 0.0250 liters of HCl. You take that and divide it. So you have 0.028 divided by 0.025. So the molarity is 1.12 molar. Okay, so this is more like what you'll see on the test, more of those two-step problems and knowing where to go in all of this. But ultimately, if you try to automatically answer the question, you're going to find that you actually have two variables and only one answer, or one known. And then, so that's why you have to find out what the other knowns are, kind of indirectly.